We continue our discussion on non-dimensionalization of Navier-Stokes equations. If you recall, last time we discussed how to non-dimensionalize the Navier-Stokes equations. So I will quickly give you a review. So non-dimensionalization of Navier-Stokes equations. We have taken a special case, a two-dimensional steady flow in the absence of body forces. So there will be no gravity or no other force. And in that case, we have the governing model partial u partial x plus partial v by partial y equals to 0, which is the continuity equation, and then rho u by partial x plus v partial u by partial y is equals to minus partial p partial x plus mu times Laplacian of u. So these are dimensional equations. We will have to convert into dimensionless form. So we want to get rid of the dimensions and units and other things. So this will be u partial v by partial x plus v partial u by partial y equals minus partial p partial y and Laplacian of the v component. So we have taken a special case which is steady, two-dimensional problem in the absence of, so our velocity field is uv and w is 0. So this is the dimensional form. Dimensional form. We want to convert into dimensionless form. Dimensionless form. So if we quickly recap, we introduce non-dimensional variables, non-dimensional variables. For length, we introduce x, that is the dimensional variable x divided by some characteristic length. So in this way, x star will be dimensionless because length के dimensions को length पे आप divide करें. So this will be dimensionless. Similarly, y steric, this will be y by L. If we have z, then z steric will be z by L. But we have x and y coordinates, two-dimensional problem. So this, now we need to non-dimensionalize velocity component. U star will be u divided by some characteristic velocity v. You could write as v infinity or some other symbol, and v star is like v over capital V. And for pressure, P steric will be P divided by, अब जो pressure के dimensions बनते हैं उनके लिए अगर हम नीचे रो v स्क्वायर सेट करें तो आप चेक करेंगे तो ये dimensionless हो जाएगा. You could use any other combination that makes this pressure dimensionless, but generally in literature this is common to take pressure divided by density times characteristic velocity and square of that. So here L is some characteristic length coming from our problem, and V infinity or V is some characteristic velocity. Again, this is coming from the physics of the problem, characteristic. And then we have converted these equations into dimensionless form. I must write directly those equations because in the previous lecture we have detailed calculations. So when you non-dimensionalize these equations, what you get is partial u steric by partial x steric plus partial v steric by partial. This is dimensionless continuity, and u star partial u star by partial x star plus v star partial u star by partial y star is equals to minus partial p star by partial x star plus mu by rho L v infinity and Laplacian of u, but with steric sign. So this is the x component, and on the similar grounds we can obtain u star v component, यहाँ पे v आ जाएगा partial v star by partial x star plus v star partial v star or partial y star minus partial b star by partial y star plus mu by rho L characteristic velocity v infinity partial to v star by partial x star square plus partial to v star over partial y star square. So these are now in dimensionless form. Dimensionless. So these are non-dimensional equations. Now, I told you we are going to define some dimensionless number, Reynolds rho L v infinity divided by u. This is called Reynolds number. This is a dimensionless number. If you put the dimension of rho, I just give you hint. Density is mass per unit volume, so its dimensions would be m L cube, और यहाँ पे हम लिखेंगे तो ml minus v. लेंथ ऑलरेडी है, तो v के डायमेंशंस क्या होंगे, मीटर पर सेकंड है इसका, तो ये एल जी इनवर्स हो गया. इसी तरह विस्कोसिटी के डायमेंशंस देखें, m l minus 1 t minus 1, और ये यहाँ पुट करके चेक करें जरा. आई थिंक यहाँ पे अभी देख लेते हैं क्या बनता है. रो के हैं m l minus 3 then l t minus 1 divided by viscosity के m l minus 1 t minus 1. So ये l स्केयर बनेगा और l minus 3 से मिलके l minus 1 t minus 1 divided by m l minus 1 t. Now you see all these will be cancelled. So m0, l0, t0. So it is guaranteed that this number that we just introduced here is a dimensionless number. This is called a Reynolds number. If you look in the equations, जब हमने non-dimensionalization किया तो ये quantity यहाँ पे appear हो रही है, और अगर आप इसको compare करें, this is the reciprocal of Reynolds number. So हम यहाँ पे लिख सकते हैं 1 over RE. ओके, ये अगर आप रिमूव करें, इसकी जगह 1 over RE नेक्स्ट स्टेप में आप लिख सकते हैं. So what you have seen, when we non-dimensionalize our governing model, there appears a number which is a dimensionless number known as Reynolds number. हमने एक simplified case consider किया है. अगर आप ग्रेविटी की टर्म लेते तो वहाँ पे भी एक dimensionless number appear होता है जिसको हम Froude number कहते हैं. अगर आप टाइम वाली टर्म भी लेते, अनस्टेडी केस लेते, तो स्ट्रूहल नंबर भी अपीयर हो सकता है जिन फ्लोज में जो है वोर्टेक्स शेडिंग वगैरह का फिनोमेना होता है. तो इन द सिंपलेस्ट सिचुएशन आपने देखा एक डायमेंशनलेस नंबर अपीयर हुआ. सो देयर आर many dimensionless numbers that come in fluid flow problems, depending what is the physics of the problem, what are the phenomena that you are considering. If you are taking some convection diffusion process, then there is a number, Peclet number, that is very important. If there is a heat transfer problem, then we have Prandtl number and so on and so forth, Richardson number, Grashof number. So there are many dimensionless numbers. So some numbers will be defined in the following section. Some important dimensionless number. So I will start with the one that we just introduced, Reynolds number. This is relevant in any flow situation, whether the flow is laminar or turbulent. It is the most important number. So denoted by RE and defined by rho VL over mu. आप just V लिख लें, V infinity, it is up to you, or V bar, whatever. So this was given by Reynolds, 1842 till 1912. This is the ratio of two forces. Actually, all dimensionless number are ratio of two forces. तो force को force पे divide करें तो dimensionless number ही बनेगा. Ratio of two forces are dimensionless numbers are ratio of two forces. So this is the ratio of inertial forces that are due to this velocity, and then viscous forces which is due to viscosity. तो आप ये forces लिखें यहाँ, उनको simplify करें, and then you get this thing. कुछ चीजें cancel हो जाती हैं. So Reynolds number is actually ratio of inertial forces to the viscous forces, where rho is the density of the fluid. This is some characteristic velocity. L is characteristic length. And mu is kinematic viscosity. Sorry, this mu is dynamic viscosity. Dynamic viscosity. And sometimes you also write Reynolds number like this. V L over उस density को आप divide कर दें, then V infinity L over nu, where nu is another coefficient. It is called kinematic viscosity. So this is again Reynolds number. So this characterizes, Reynolds number characterizes laminar and turbulent flows. If Reynolds number is small, flow is termed as laminar, जिसमें आपने देखा streamlines or straight lines. They will not intersect each other. If Reynolds is high, then the flow is termed as turbulent. Again, this small or large or high value depends upon the flow configuration. कभी Reynolds 100 भी high consider किया जाएगा, कभी जो है Reynolds 500 को small consider किया जाएगा. Again, ये physics पे depend करता है और geometry पे depend करता है. For a simple channel flow with no obstacles, if Reynolds is approximately 2200, till this range, flow is called laminar, and after that, flow will be turbulent. And of course, there will be some transitional portion, 2200 to 2300 or whatever. These are some approximations. So this is very important number. So it differentiates whether the flow is turbulent or laminar. So it is the ratio of inertial forces over viscous forces. If inertial forces are dominant, then this will be large. If the viscous forces are dominant, Reynolds number will be small. For highly viscous fluids with low velocities, the Reynolds is small, and we know these flows are called slow flows. Okay, we move towards another dimensionless number, which is the Froude number. So it was developed or defined by William Froude from 1810 to 1879. This is ratio of inertial to the gravitational forces. Inertial forces to the, as I already told you, all these dimensionless numbers, they are ratio of two forces. So force को जब force से divide करते हैं, you get dimensionless number. So inertial forces to the gravitational forces. अभी जो हमने डेरिवेशन की थी लास्ट लेक्चर में और आज भी रिकैप किया, हमने ग्रेविटी को निगलेक्ट किया था, लिहाजा ये नंबर अपीयर नहीं हुआ. अगर हम ग्रेविटी भी लेते तो ये अभी जो मैं लिखने लगा हूँ ये टर्म भी अपीयर होनी थी. So इसको आप मैथमेटिकल फॉर्म लिखते हैं. Froude number is denoted by FR, which is the ratio of inertial forces to the gravitational forces. तो रेनॉल्ड नंबर में ग्रेविटेशनल फोर्सेस की जगह विस्कस फोर्सेस थी, वहाँ विस्कोसिटी थी, अब यहाँ ग्रेविटी आएगा. सो इनर्शियल फोर्सेस आर रो यू स्क्वायर एल स्क्वायर डिवाइडेड बाय ग्रेविटेशनल फोर्सेस. फोर्स बना रहा हूँ मैं, ठीक है, ये फोर्स के यूनिट्स बनेंगे. बाय द वे व्हेन यू विल सिंप्लीफाई यू नीड टू रिमेंबर दिस विल बिकम यू स्क्वायर ओवर जी इंटू एल. अगेन यू इज सम कैरेक्टरिस्टिक वेलोसिटी, आप वी इंफिनिटी भी लिख सकते हैं, ठीक है. अगर आप रेनॉल्ड नंबर के साथ कंपेयर करना चाह रहे हैं या वही नोटेशन देना चाह रहे हैं तो आप इस u की जगह v इंफिनिटी. बट मैं ये बार बार चेंज इसलिए कर रहा हूँ कि आपको ये पता हो दिस इज सम कैरेक्टरिस्टिक वेलोसिटी, नोटेशन इज नॉट इम्पोर्टेंट. सो u स्क्वायर बाय जी एल. इसमें अगर आप अब u के डायमेंशंस पुट करें, उसका स्क्वायर लें और g के डायमेंशंस जो कि ग्रेविटेशनल एक्सेलरेशन है उसके डायमेंशंस पुट करें, l ऑलरेडी लेंथ है, तो यू विल सी कि ये इसमें m0 L0 T0 जैसे मैंने रेनॉल्ड नंबर में किया था. दिस यू कैन वेरीफाई बाय योरसेल्फ. वेरीफाई. सो यूज कैरेक्टरिस्टिक वेलोसिटी, अगेन g इज द ग्रेविटेशनल एक्सेलरेशन, ये कैंसिल हो जाएंगे, l स्क्वायर और l क्यूब नीचे जो है l वर्ग बचेगा. ये दिस इज कॉल्ड फ्रूड नंबर. So this is important in surface flows. Important in surface flows. Maybe at your higher level you have some research problem in computational fluid dynamics and you might be using this number in your simulations. So you will be setting fluid as 0, 1, 2, 5, 10 because this is a dimensionless number. अगर inertial forces dominant होंगी तो fluid number बड़ा होगा, अगर gravitational forces जो हैं वो dominant होंगी तो fluid number will be small. Then we have third number, which is Strouhal number. Strouhal number. This is important in oscillating flows or periodic flows. And Strouhal number is given by Strouhal, the scientist, and denoted by St. This is omega L over mu u. So omega is frequency of vortices, vortex shedding. So if you have some channel and with some obstacle and fluid is coming to this channel, if this is very high speed flow, then after this there will be some vortices generated and they will be traveling downstream the channel. So in the form of vortices, the flow will be happening. So what is the frequency of those vortices? This is the omega. L is characteristic length and u again are u infinity, whatever you want to write. This is some characteristic velocity. So this is important in time dependent flows. तो हमने जब नॉन डायमेंशनलाइजेशन किया था हमने स्टेडी लिया था, इसलिए ये नंबर भी अपीयर नहीं हुआ. Okay, the fourth one is Peclet number. Peclet. So this was introduced by J.C. Peclet. It is ratio of convective forces to the diffusive forces. So this is ratio of convective forces to the diffusive forces. After simplifying, the form of Peclet is VL over D. So V is again characteristic velocity, or if you wanna wish, you wanna write this V infinity characteristic velocity L characteristic length, D is diffusion coefficient. D is diffusion coefficient. If convective forces are dominant, this velocity is high, Peclet would be high, Peclet will be large for high value of this velocity. And Peclet will be small if D is very large. ये जो diffusion coefficient है, ये ज़्यादा strong होगा, dominant होगा, तो of course Peclet number जो है वो small हो जाएगा. It's very easy. अगर numerator strong है, तो ये large number होगा. अगर ये strong है, तो फिर ये small number होगा. So D is called diffusion coefficient. Again, for gases, diffusion coefficient is different. और for liquids, इसमें आप किस चीज को डिस्कस कर रहे हैं, कंसंट्रेशन वगैरह किस केमिकल की है, उसकी डिफ्यूजन किस रेट से हो रही है, तो वो भी डी उस हिसाब से होगा. The last number I would like to define here is the fifth one, the Prandtl number. Again, this list is very big, maybe 200, 300 or more than that. We have dimensionless number that appear in our problems, because we don't only have the fluid mechanics problem, we have structural mechanics problem, we have electrical circuit problems and so on and so forth. तो जिस तरह की physics है, problems है, models हैं, जब आप उन equations को non-dimensionalize करते हैं, तो ये certain special किस्म के dimensionless number appear होते हैं. Prandtl number. This is T. So this was introduced by German physicist Ludwig Prandtl. So German physicist Ludwig Prandtl. So this is ratio of momentum diffusivity over thermal diffusivity. Momentum diffusivity over thermal. As the definition says, we have some thermal considerations. So जिन प्रॉब्लम में आप एनर्जी इक्वेशन भी ला रहे हैं, टेम्परेचर को भी कंसिडर कर रहे हैं, तब ये अपीयर होता है. So Prandtl number is nu, that is momentum diffusivity, ये जो viscosity की वजह से है, and then alpha is the used symbol in the literature for thermal diffusivity. So this is used in some heat transfer problems. If in future, if you are working on some heat transfer problem, you will come across this number after non-dimensionalization. So I have defined here the 4 dimensionless number. You need to recall these numbers. You need to see their formulas, and you need to verify that they are already dimensionless. मैंने रेनॉल्ड्स नंबर को बताया आपको कि आप अगर इसमें वो सारी पुट करते हैं डायमेंशंस, तो आपके पास ये सिचुएशन है, और बाकियों के लिए आप जो है ये वेरीफाई कर सकते हैं. So that was the topic of non-dimensionalization. We started from steady 2-dimensional Navier-Stokes equations in the absence of gravity or body forces. And when we non-dimensionalized those equations, we have obtained a non-dimensional number, Reynolds number. And then I have further defined certain other dimensionless numbers. Froude number, if there are gravity forces, if there are some periodic phenomena, time-dependent flows, we get Strouhal number. And then for convection diffusion equation or convection diffusion processes, we get Peclet number. This is very important in convection and diffusion procedures, processes. So if Peclet is high, it means the convection is dominant. If Peclet is low, the diffusion process is dominant. So this is for diffusion. This is for convection. And the last one was Prandtl number given by Prandtl. This is momentum diffusivity over thermal diffusivity. So that is the end of this lecture. And in the next lecture, we will see what are the advantages of this non-dimensionalization and what we mean by geometric similarity, what is meant by kinematic similarity, and what is meant by a dynamic similarity. So there will be three types of similarities when we non-dimensionalize this equation from a original model. We will be developing some prototype of that model जिसके अंदर ये तीन तरह की similarities हम discuss करेंगे. Thank you very much. Allah Hafiz.